if you're ready, then you can go ahead with the robot executive design summary or presentation, whatever you want to do.
All right, well, we're Team Borexus number 9852 in North Carolina. This is Sarah. This is Jacob.
This is Esperanza. This is Zach. This is Sam.
That's Luke.
That's Jackson.
This is Jacob.
All right, and well, we started off like the beginning of the year with 2 EV3s, and it was kind of hard to get like all 9 people like working on like trying to program one robot. So we fixed that by like splitting up into Team 1 and Team 2, and we each had like our own robot to program and everything. And then within those groups, we were programmers and mechanical. And just mechanical got to like build the robot and put the attachments and everything on, and then programmers did coding and programming.
Mechanical and programming both met together, and it worked well because the programming people were able to tell mechanical people what kinks needed to be fixed in the robot and everything. And then the mechanical people went on to fix those with digital designer, and we just since there were 2 teams, we of course split them into who was good, like who had the kind of building mindset and who had the programming mindset.
Like we had a problem with the programmers and the mechanical people needing a robot at the same time. So we used a program called for the computer called Lego Digital Designer. It's where you can like you have a whole bunch of Lego bricks and you can build basically whatever you want. And so we use that and you can print out instructions. So we use that to work on the robot, the mechanical people did, and then they can print out the instructions so that when the mechanical people are done, they can work on the robot and they don't have to like
Okay.
Our mechanical motto is keep it simple, keep it sturdy. We have like 1 or 2 attachments on the robot because having more and more attachments to put on every time for like a mission model takes up too much time. So practically, pretty much when we hit the table, all we have to do is just press the program and go instead of having to take up all these pieces.
Another thing we used this year was interlocking pieces. That makes everything like more durable. The way I came up with a little definition of interlocking pieces. It's every piece connects to every piece, and that's exactly what it is. You just actually real quick. This is an example of interlocking pieces. See like these 2 beams down here that hold all this stuff up here, and these pieces that just everything meshes together. So that helped us a lot this year with durability, and that's what makes the robot the best.
So you like this?
Okay. So I have a mission that you can demonstrate for us?
Sure.
Okay.
We realized a problem whenever we were doing out a base. So we put 2 light sensors on it, and we lined up with the black line when it came out, so it would always be accurate.
Okay.
So yeah, so that's what you'll see whenever it like lines up and then it beeps 2 times.
That was another thing that we noticed is on the practice table it didn't work, but on the judging tables it did work, so we just didn't mess with it. We just left it the way it was, so it was on the judging table. We had a big problem with the gyro sensor this year. We used it last year and we had a lot of inconsistency problems. Like the plus or minus 3 degree like error. We first saw that online on the spec sheet. We had a copy of it and we put it in the floor if you want to look at it. But we saw that and we didn't really just want to do anything that's word for it, so we ran a test and found out that it was totally true. We never really did find out if it was just the momentum of the robot turning. It was just after it had stopped, the robot would keep on going because of the momentum, and then the gyro would see that and would say that it was a 92 or something. We never figured out if it was the gyro sensor or if it was just the gyro sensors are stopping the momentum was taking it off. But we did do tests. Either way, we found out that it was inconsistent. The way that we accounted for that error is we created a my block. The name is gyro, and basically, if you put it in there, we made a parameter, we told it to go 90, it goes up, it goes for, like you said 90, it would go 90, and then it would see that it's 93. We would see that it's 93 degrees off, and it would go very, very slowly the other direction, and it would see that now it's at 90. So then it's good and we keep going. We also had a problem with backlash. There's a printed out a sheet there with a picture on backlash. Backlash is just loose, inconsistent, like the gears inside, if you notice these things turn, and it's the wheel, the motor's not actually turning, it's just the wheel is. That's due to looseness of the gear connections. One time we opened up the motor and we looked inside of it and you could actually see all the looseness in the gears. And that would create problems because if you just set the robot down, this wheel could be forward a little bit, this one could be backwards a little bit, and so when you start off, you could go in either direction. In the beginning, we knew that was kind of a problem, so we would just pull it back like this, and it would tighten up all the gears. But then out on the board, you can't do that, so we created a my block just telling it to go unregulated with the unregulated motor blocks. The difference between a regulated motor block and an unregulated motor block is the regulated is the speed. So even if you tell it to go 75, let's say that if you told both motors to go at 75, then it's like this. This one can keep going 75, but it's going to see that this one's not going anywhere, so it's going to rank up the speed so that the power so that it can go the speed that you told it to. And with the regulated motor block, it's just the power. So if you tell it to go 75, it doesn't go at the same. So that's why we use the unregulated motor blocks for that problem, is because we didn't want it to, we just wanted it to be the speed. So basically what it does is it
I hate to interrupt you here, but we got to get a lot of questions in, so you're going into a lot more detail than. Okay, so what was your strategy to determine which missions you were going to accomplish?
Well, really what was close and what was, it's not incredibly hard. Like this one, we were thinking we could do it, we couldn't fit the robot back there, so we didn't really bother with it. We probably will in the future.
Because what point, and what worthy, like if it's not, if it's a really hard mission and it's not worth that many points, then don't do it.
So if you're on the competition floor, if your robot does perfect, what do you expect the score to be?
230, that's our target. There's definitely a difference between target and what you actually get, because you have a program to get that much, but
so you theoretical max is 200.
yeah, that's our target.
So what other missions are you trying to make?
We have this one that was programmed to do it, but pushing the model into here, pushing the slider, getting everything, doing the shot. And
You said getting. How would you know which one to get?
We started it's the same program. It's just it's waiting for either this button to be pushed or this button to be pushed or this button to be pushed. The middle button is push below.
Oh, okay. So you push this in, the robot goes back, and then you come
yeah, and then it comes back and does the same. It's the same